Hello, and welcome to another video in this series as we learn the basics of Lean in order to write simple proofs. Today's quite a milestone because we're going to write our own lemma. We're definitely grown-ups now. In the last few videos we've been practicing applying a definition and making use of Mathlib lemmas. That's an important thing to do because most proofs will make use of Mathlib lemmas and theorems. And that's kind of the bread and butter of writing Lean proofs. But sometimes it's useful to be able to write your own, and there might be a couple of reasons you want to do that. One is that the idea that you want to encode into a lemma just doesn't exist in a convenient form in Mathlib. So for your own convenience, you want to write a lemma and then use that lemma lots of times. It could also be that you've made a new discovery and you want to use Lean to check that your proof is correct, that your thinking is correct, in which case congratulations, you've made progress in the world of mathematics. But I suspect far more common will be the idea that we want to create a lemma for convenience because Mathlib doesn't quite have what we want. And that's what we'll do today. We'll actually create a convenience lemma which encompasses an idea, which is true, but Mathlib just doesn't happen to have it in that form. I should say that, and I've said it before, the distinction between lemmas and theorems in Mathlib in Lean isn't significant. So in the real world of mathematics, lemmas are considered small and theorems are considered big in the sense that they encompass an idea that changes or moves forward our understanding of mathematics, whereas lemmas are kind of the bricks that build the house, as it were. But in Mathlib, in Lean, the distinction isn't that clear, so it's fine to use them interchangeably. That's fine. And you'll see in Mathlib itself, if you look at the definitions, some things which are small and they're called theorems, and it's kind of difficult to work out why is it called a theorem, not a lemma, but that's fine. It's something not to worry about. So before we dive in, let's draw a picture. So sometimes when we're doing proofs, it's useful to be able to split the number line into two. So the number line might be the real numbers, 0, 1, 2, 3, and so on. And you'll have negative numbers as well, but you'll also have numbers in between the whole numbers. So you might have 1.3, and you might have irrational numbers, pi somewhere here, and so on. And you might want to split and say we want to split the real line into two. So we might have a first one which goes from 0, or actually all the way up to so all the way up to minus, or say up to 3. So all the numbers up to 3, and then the second set will be 3 upwards. Then we have to think about whether we include or not include 3. So we might say this does include 3 and this doesn't. So we might do that. And there's different notations. You might see something like minus infinity up to 3, and then not including 3 up to infinity. So you might see things like that. We're going to stick with simpler natural numbers. So if we have the natural numbers, then you don't have negative numbers, 1, 2, 3, 4. You don't have numbers in between these things. They just don't exist. So between 1 and 2 there isn't a number by definition of natural numbers. So the axioms which define the natural numbers say that if we have 1, then the successor is, we call it 2, and it's the only successor. There's nothing that's larger than 1 but less than 2. So 2 is the unique successor. Just going into a bit too much detail there probably, but it's an important point that for the integers as well, there's nothing in between. And it's useful to think about that when we split. So we might want to split this and say 0 to 2 inclusive, and then 3 up to infinity. So that will split it into two sets, this set and this set. That can be useful. If we wanted to do this more generally with the natural numbers, let's say 0, 1, 2, and so on. If we picked picked a number b, the next one is b plus 1. Now, if we say we've picked b in the natural numbers, then any other number a has to be in this set or in this set. So we can say, given a natural number b, we've picked one, then any other one, a, is either less than or equal to b, or b plus 1 is less than or equal to a. That's the general idea that we want to encapsulate in a lemma. Now, Mathlib actually doesn't have that idea. It has a related idea. It has the idea, I think, if I recall correctly, that a is less than or equal to b, or b is less than a. I think that's in there. We'll check, we'll find out. It's similar, and that's probably why this one doesn't exist. I like this one because it's symmetrical. They're both using less than or equals, whereas this one is using less than or equals and then less than. But they are equivalent only if you're thinking about natural numbers and integers. This one actually is more general. If you look at it, you'll notice that it's actually true for real numbers as well, but we won't go into that today. So this one can be convenient. It's a convenience lemma over that one. So that's what we're going to write today. Great, let's get back to doing it. So this is just a picture that encompasses that idea. Pick a b, natural number, then any other one, any other number a, is either in this set, a is less than or equal to b, or it's in this set, b plus 1 is less than or equal to a. That's kind of visualization of what we're saying. So this is the lemma we're going to create. And just to test it, let's say b is 7, but we leave a unspecified. It says that a is less than or equal to 7, or 8 is less than or equal to a, which makes sense. Great. So how would we do this? Well, we're not going to do it from the axioms up. We should make use of Mathlib lemmas in order to prove our one. So let's write this out. We want to prove this proof objective. This is our lemma that we want to prove. A is less than or equal to b, or b plus 1 is less than or equal to a. We're going to make use of two known lemmas that are in Mathlib, which will actually make our proof really short, but that's okay. We did mention, didn't we, in our picture, this one here, that there is a Mathlib lemma, a is less than b, or b is less than a. So that's less than or equal to, and that's less than. So that actually does exist in Mathlib, and we'll make use of it. You can see it's really similar to what we want. Instead of b plus 1, they've got b. Instead of less than or equal to a, they've got less than. And that will help. That short distance between the two will help us. This one is almost there. And how do we make that bridge the gap? Well, there's another lemma which says m plus 1 is less than or equal to n if and only if m is less than n. That can make sense. Let's illustrate that in case it doesn't. So m is less than or equal to n if and only if m plus 1 less than n. Let's illustrate that with some numbers. So 8 is less than or equal to 10 if and only if 7 is less than 10. That's kind of obviously true. Nothing complicated there. Let's get closer to the edge case. Let's say 9 plus 1, which is 10, is less than or equal to 10, which is the same as 9 is less than 10. That's the edge case, that's the interesting case. So that just to illustrate that idea, it's saying that if you've got the number line, if that's n, then m plus 1, that's m plus 1, so that's m, and then that's m plus 1. That's going to be less than or equal to n, and as these get closer, we're testing the limits of that idea, and the closest you can get is if that m plus, that's m, and then n plus 1 is actually equal to n, which means m is less than n. So we're going to make use of those. So how do we do that? Well, if we apply this lemma to this, what do we get? Let's write this down, because I think if we write it on a blank piece of paper, it'll be easier to see. A is less than or equal to B, or B plus 1 is less than or equal to A. We've got a couple of lemmas in Mathlib. One is A is less than or equal to B, or B is less than A. And the other one is m plus 1 is less than or equal to n if and only if m is less than n. So how are these going to help us? Well, that plus 1 looks interestingly like that one. In fact, b plus 1 less than or equal to a looks just like that. So if we apply this lemma to our proof objective, what do we get? We get that turned into a is less than or equal to b, or these are equivalent. Remember the if and only if? That means b is less than a. That's what this is turned into. So that's equivalent. And then we look at the other one and say, well, that's exactly the same thing. So that's equivalent. So we've started with our proof objective. We said it's equivalent to, so that's 1, equivalent to this, and that's also equivalent to something that we know to be true. So then we can say this is proven. That might sound a little bit weird, so let me write that down in a different way. We have our proof objective. We've said it's equivalent to something else, let's call it x, and then we've shown that's equivalent to a lemma that we know is true. So if that's true, and this is equivalent, that's true. If that's equivalent, then our proof objective is true. That's the idea. So have a look at that in slower time. If you want to look at the blog, that also narrates that a little bit more slowly. It may feel like this is going backwards, but you'll find again in Lean, often we are encouraged to manipulate the current goal, which can be the proof objective, whereas in pen and paper proofs we tend to be constructive. We tend to move from known small facts to build up to the conclusion. But in the world of Lean, sometimes you'll see equally valid proofs that actually take a proof objective and then decompose that or take that to another equivalent truth which is known to be true, and we prove it that way. So we'll have a look at we'll actually write the lemma and the proof, and we'll do it live so we can kind of talk through what's happening. I'm going to be using for this video the online environment, live.leanlang.org, which allows you to use Lean without installing anything. But if you want to install your own, that's fine. And the Visual Studio Code with the Lean extension is quite a nice way of doing it. So, as usual, we import the Mathlib tactics. this time we're not saying example, we're saying lemma. So what that does, it says we're about to create something that's going to be proved, and we want to give it a name. That's the name. And with example, we didn't have a name because we didn't really care about using that result afterwards. But with the lemma, we want to prove something and then use that afterwards. It's reusable in the same way that we use Mathlib lemmas. We want to create our own lemma to be usable. So we have to give it a name. So there's a convention that says lemmas that are about natural numbers should have a nat dot prefix. So nat dot, and the kind of fancy way of saying that is that our lemma is in the nat namespace. That's kind of a way of organizing lemmas. But for now, we can just think of it as, if you look at something with a nat dot in front of it, it means the lemma is about natural numbers. So if it was about integers, it might have int. So nat is what we're sticking with. We'll give it a name that kind of follows the naming convention. As I say, the naming convention isn't ideal. It's one of the areas of Mathlib that I think hopefully is improved in future. But this kind of represents our idea, which is a is less than b, or b plus 1 is less than a. That's our proof objective. And our lemma will require two numbers, and they are round brackets, and we'll talk about that in a minute. In most of our previous examples, if not all of them, we've used curly brackets around variable declarations. Round brackets means that anyone using our lemma has to provide those parameters. So you can't use our lemma without providing a and b. So if you know about computer programming in the general sense, it's mandatory parameters to the function in some way. Right, so otherwise it looks kind of standard. We've got the fronty bit, we've got the variables, we've got the proof objective, and then we're going to prove it. Now you might have seen this thing called sorry in elsewhere. It's just a way of saying, it's telling Lean to ignore the errors, and it's saying, yeah, mark it with a warning that we haven't completed the proof, but don't kind of let that break the flow. So it's a way of saying we'll come back and finish this later. So let's look at the all messages saying declaration uses sorry. So it's not forgotten that we haven't finished our work, but it's a way of sort of saying, well, don't break everything just because we haven't done it yet, because you can still make use of this without completing it properly. What's the second bit of code? Well, whenever you write lemmas and definitions, as we'll see later, it's considerate to provide a minimal example showing how it's used, just to illustrate it. Not everyone does that. I actually don't think the Lean Mathlib libraries do that, but I think it's a good idea, particularly for your own code. So it's always good to have a little illustrative example that's really minimal. You don't want to go overboard. So we'll kind of provide that as well. So we'll say that for any natural number c is less than or equal to 2, or 3 is less than or equal to c. That sounds obvious, but our lemma will help prove that. So what are we going to do here? Well, we're going to make use of the Mathlib lemma, just as we did in our maths proof, to rewrite this bit. So let's rewrite the goal. And do you remember, if we said at something, like at h, that would rewrite the hypothesis, but we're not doing that. We're just rewriting the goal. So what's the lemma we're going to use? It's this one, isn't it? Nope, it's this one we're going to use to rewrite that as a less than. So we need to find a Mathlib lemma that does that. And it took me a bit of searching, but as I say, it's not ideal. But I did find one in the end, and it's this one. And you can see it also has a nat in front of it to say it's about natural numbers. So add one le if. So what does it say? Oops. it says m and n are natural numbers, then n plus 1 is less than or equal to m is equivalent to n is less than m. This was in our pen and paper proof. So which direction do we want to apply it? It's in the forward direction. That's fine. So we don't need to think too much about that. So let's copy and paste that into there. Right, so let's see what that's done. So in the info view, this is a good idea always to use the info view to keep track of what's going on. Before that's applied, our proof objective is a is less than b, less than or equal to b, or b plus 1 is less than or equal to a. Once that's applied, it's transformed into the equivalent a is less than or equal to b, or b is less than a. And we said that actually there is an existing Mathlib lemma that says this, which is known true. So we've arrived at something known true. So we should be able to just say, apply that lemma to resolve that goal. What is that lemma called? It's actually called LE or LT. And we have to provide two numbers to it. So let's look at this. Let's search for it. Let's search for it in the Google. There it is. And it's saying that A and B are numbers. Don't worry too much about all this stuff right now. It doesn't even say that they're natural numbers or integers. We can read this for now as being numbers that have an order, which also means the real numbers as well, and rational numbers, but not complex numbers. So those numbers, if you have two of them, it's true that A is less than or equal to B, or B is less than A, which is where we've ended up when we were here. So we can apply that, and that resolves the goal. Why did we provide those two parameters? Because they're required by the round brackets. And that completes the proof, actually. And because this is an exact match, we should say exact, just to be more strict than we need, than absolutely necessary. The stricter we can be, the better, because it reduces errors, or it reduces the delaying the identification of errors. We've talked about that in previous videos. Great. So actually, in just 2 lines, we've proven this lemma, and that shouldn't be a surprise, because we're making use of a Mathlib lemma that was almost there. This Mathlib lemma is very similar to what we're trying to prove. So what we've created is a convenience lemma. So let's apply it. So we've got this thing we want to prove, and our we think we can just apply our lemma, can't we? Which is nat.le or successor le. We need to provide 2 numbers. What are they? Well, let's look at our definition. Our lemma takes 2 numbers and creates this statement, this proposition, A and B. Now, if we compare this with this, what do we need to instantiate? Well, here A is C, so C, and here B is 2, because here B plus 1 is 2 plus 1, 3, yeah. So that should complete the proof. I've misspelt it, didn't I? There we go. And does that work? It does. And can we do exact? Yes, we can. So we've proven that in 1 line. Great. So we've written our own lemma. Convenience lemma, you can see, wasn't absolutely necessary because there's a very similar Mathlib lemma, but the idea was to just talk us through the process of creating our own lemma, giving it a name, using lemma, doing the proof, and practicing making use of existing Mathlib lemmas. Fantastic. So you can read about that in the slides or the blog, which talks through the points we've just talked through, does it in writing. So you can see the point about nat prefix, We could talk about the naming convention, which, as I said, is not ideal, but we have what we have. And the importance of round brackets, meaning that those parameters have to be supplied. We used a Mathlib lemma, which is similar to our own. This one, it's the one we want to prove. That was the difference. So we bridged that difference using another lemma, using that one. Great. And we also looked at the info view just to see the see the effect of that rewriting. Let's do that now, just to see it ourselves. So before this is applied, our goal state should not have changed. Our proof objective is a is less than b, or b plus 1 is less than or equal to a. After applying that, it's transformed that b plus 1 is less than or equal to a to b is less than a. That's what we wanted. So it's useful to observe that in the goal state, in the intro view. That's really a helpful thing to be able to do. So that's why I include these, is just to give you practice in following what the what Lean thinks is, what Lean knows is happening versus what you think is happening, just to check. Great. So as always, we have what we call an easy exercise. It's not meant to be patronizing. The idea is that we don't choose maths problems that are difficult or complex or algebra torture. The idea is to keep the math simple so we can focus on practicing Lean. And lots of the exercises are very similar to the examples given anyway. So the idea here is, the task is to write a lemma for integers and to show that this is always true. Now you notice this is exactly the same as what we wanted to show with our lemma, so there's no change there. So the only thing that's changing is the example only applied to natural numbers, but the one you're going to write applies to integers. So hopefully that's not a big change. In fact, I'm suggesting you can copy the lemma and modify it, and then prove it works with a minimal example which involves negative numbers, because these wouldn't have been valid with our lemma, because that was only for natural numbers. So c is less than or equal to 5, or minus 4 is less than or equal to c. So have a go at that. It should be a small change, but if you find it, then that's good, because it shows you, gives you an insight into the difference between lemmas for integers and lemmas for natural numbers. So have a go at that. Any problems, do comment, and we'll have a chat about it. Cheers. Bye.